Happy Wednesday. I didn't bring my umbrella, so you can expect that we will all get wet when we leave to go to our cars after class. That's what's gonna happen. I'll try to remember my umbrella. Your Infinity homework is due Friday. Quiz day is Monday. After today, you'll be able to do all the homework. Friday's just a homework answering day. So let's try it. So I'm going to start with this chart that sort of summarizes everything we should know about functions, derivatives, and second derivatives. Okay. So the first column has all the properties of the function. The second column has all the properties of the first derivative, and the third column has all the properties of the second derivative. So we know that when a function is increasing or decreasing, the first derivative is positive or negative because it tells us the slopes of the tangent lines. We know that maximums and minimums happen at critical points when the derivative is 0. We'll come back to this part. Increasing or decreasing is the same as going up or down. If the function's going up, that means that the function is increasing, which means that the first derivative is positive. So if you were looking at a graph of the first derivative, it would be above the x-axis. Positive numbers are when the graph is above the x-axis. If the original function is going down, then the graph of the derivative will be below the x-axis. So this is where it gets hard because we're going to look at graphs of functions and talk about the first and second derivative. We're going to look at graphs of derivatives and talk about the function. So we want to be able to go sort of both ways. So if you're looking at a graph of the derivative, you're sort of looking at these bottom 4 pieces in your list. Where is the graph above the x-axis? Where is it below? Where is it going up and where is it going down? That's going to tell you these pieces of information about your function, okay? So if you're looking at a graph of the derivative, if it's above the x-axis, the original function is going up. If it's below the x-axis, the original function is going down. If the graph of the derivative is increasing, the original function is concave up. If the graph of the derivative is decreasing, then the original function is concave down. Because concavity is determined by the second derivative. It's concave up when the second derivative is positive. It's concave down when the second derivative is negative. So we're going to do a Desmos activity. It's not going to take long. It's a matching. But I want you to remember these 4 shapes. This is what we ended with on Monday, these 4 shapes, right? These 2 shapes put together we called concave up. This side was concave up and decreasing. This side is concave up and increasing. These 2 over here, if we match them together, would be concave down. This is concave down and decreasing. This is concave down and increasing. What I want you to think about is if I gave you this shape, would the first derivative be a positive number or a negative number? This shape up here, negative because it's decreasing, right? If I gave you this shape, would the second derivative be a positive number or a negative number? Positive because it's concave up, right? The second derivative tells you concavity. So this top left corner, for instance, is concave up and decreasing. The first derivative is a negative number because it's decreasing. The second derivative is a positive number because it's concave up. So what you're going to see in the Desmos activity, make sure you choose the right one because I think there's 2 up there. You're going to choose the one on graphing. What you're going to see in the Desmos activity is cards. They're going to have one of these 4 shapes on them, and they're going to have a list of properties. The properties are going to be the first derivative is positive, or the function is increasing, or the second derivative is positive, right? And you're going to match them to the picture, okay? So you're going to have 2 matches, 1 picture, 1 description, match them together. Student.desmos.com, PHSV63. Someone has to have the job of reminding me, just sorting. Okay, so here's the next kind of problem we're going to see. This says, here's a graph of the function, and it wants me to sketch the graph of the derivative, okay? Here's a graph of the function, and it wants me to sketch the graph of the derivative. So we're gonna go both ways. We're gonna have graphs of functions, we're gonna make derivatives, we're gonna have derivatives, and we're gonna make functions. Both ways, that's what we're gonna do. Here's the graph of the function. I want to sketch the graph of the derivative. What does the derivative tell you about the function? The slope. So when this function is going up from -infinity until -3, the derivative should be what kind of number? A positive number. When this function is going up, the derivative should be a positive number. So here and here. So when I'm drawing the derivative, this is -3, -2, -1, 1. The derivative should be here and here, above the x-axis. Yes? When the function is increasing before -3 and between -1 and 1, the derivative should be a positive number, meaning above the x-axis. When the function is decreasing, here and here, the derivative should be what kind of number? Negative below the x-axis. So down here and down here. What do we know about the derivative at the maximums and minimums? It should be 0. At these critical points, at these maximums and minimums, the derivative should be 0. Okay, so the derivative is 0 at max and min. It's negative when it's decreasing and it's above the x-axis, or positive when it's increasing. Okay, so that's really all I know, right? I know I need a function that falls in the pink and green areas and crosses or touches the x-axis at those 3 dots. I don't really know a lot other than that. So I'm just going to draw a function that crosses the x-axis at those 3 dots and lies in the pink and green areas. So I made it cross the x-axis at -3, 1, and 1. I made it be above the x-axis in the pink areas and below the x-axis in the green areas. If you think about it, this guy here, this function has degree 4. We know he has degree 4 because his 2 ends go in the same direction. So he has even degree, and he has 3 humps. So we think degree 4. When you take the derivative of a degree 4 polynomial, what degree would it have? If you take the derivative of a degree 4 polynomial, like x to the 4th, what degree would it have?
X to the 3rd.
X to the 3rd, like cube, right? And this guy is a cube. His ends go in opposite directions. He crosses the x-axis 3 times, and he has 2 humps, right? So we kind of go down. Oh, you still drawing? You're okay? You looked like you were still drawing. Okay, so there's lots of ways to organize your information. I'm a big fan of the sign chart. And the thing I like the sign chart for is because it helps me keep everything organized. And then I can just use those 4 shapes that we just practiced and mush them together, okay? So sign charts are an easy way to represent specific behaviors. Here's the sign chart, and here's what they told me. The sign of the derivative. So this sign chart is all about the derivative. It says from here until 0, the derivative is positive. Between 0 and 4, the derivative is negative. From 4 to 6, the derivative is positive, and bigger than 6, the derivative is positive. This should look very familiar because this is the sign chart from the example we did on Monday. where we had to draw that picture, okay? So it's increasing. If you look back at your chart, summary chart today, it's increasing up until 0. It's decreasing from 0 to 4, and it's increasing afterwards. If you remember the example from Monday, they also gave us the information that f prime of 0 was undefined. So we needed a cusp or a corner there, and that at 6 and 0, it was flat points. So from this sign chart, we drew a graph that looked like this. So this is 0. This is 4. I did a bad job with that. And this is 6. Should have made it line up there, but I didn't. So a sign chart is a really good way to organize information, especially when you get to information that has like things about the first derivative and the second derivative and the function, right? A lot of times we're going to get information about all 3 pieces. Okay, so here's a really big sign chart, a big one. It has tons and tons of information. The top row tells me my intervals, right? If I read this top row, I can think about what my important points on the graph are. I can see that at x equals -1, things happen. At x equals 1, things happen. At x equals 2, things happen. At x equals 4, things happen. And at x equals 5, things happen, right? From before -1, the first derivative, this column, this row here is my first derivative row. And then the row below that is my second derivative row. Before -1, the first derivative is positive. What does that tell you about the function if the first derivative is positive? It's increasing, right? Before -1, the second derivative is negative. What does that tell you about the function? Concave down, right? So before -1, the first derivative, the function should be increasing and concave down. Which of those 4 shapes is an increasing concave down shape? Which of those 4 shapes is an increasing concave down shape? So what I know is that before -1, the function should have this shape, increasing concave down, okay? Tell me what happens between -1 and 1. It's decreasing because the derivative, the first derivative is negative. It's concave down because the second derivative is negative. So I need a shape that is decreasing and concave down. So look at your 4 shapes and hold me up. What does decreasing, concave down look like? Right? Decreasing, concave down looks like the hill of the roller coaster, right? Okay. The funnest part. Like that. Yeah. So when I'm drawing this graph, I'm just going to be able to take these shapes and match them together. Okay. All right. Let's try to answer these questions. It says, use the sign chart to determine the intervals where the function is increasing. So where is my function increasing and what do I look at to know that? My function is increasing when f prime is positive. So which intervals is my function increasing? From -infinity until -1 and from +5 to +infinity. We looked for f prime positive. Okay, the next part says, where is the function decreasing? You look for where the derivative is negative. So here, 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 here. So f prime negative. I can squish these together, right? So from -1 until 2, -1 to 2, and from 2 all the way until 5. What does that mean happens at 0? I'm sorry, not at 0, at 2. What does it mean happens at 2? The function goes down, then the derivative is 0, and then the function goes down some more. So the function's going down, the derivative is 0, and then the function goes down some more. Down, derivative is 0, function goes down some more. It's one of those horizontal tangent lines like we get in x cubed. So it's going to look something like this probably. Okay, where it gets to be 0 there. Okay, extrema. What do we say extrema are? Max and min. Yeah, good. Extrema are max and min. Okay. I think that if we draw, can you tell me where the extrema are? An extrema is where the derivative is 0, right? But more importantly, what has to happen? It has to be a top or a bottom, right? So is x equals 2 an extrema? No, because the derivative is negative on both sides, right? At x equals -1, the derivative is going, the function's going up, and then it's going down. So what happens at x equals -1? There's a maximum at x equals -1. X equals -1 is a maximum. Where else should you look? At x equals 5. It's going down, negative, coming up, positive. Minimum at x equals 5. So remember, extrema happen at critical points, which were at -1, at 2, and at 5. 2 got excluded because the derivative didn't change sign there. I'm going to put a page break in here because I want to draw the picture of this at the end. Okay, let's talk about concavity. Concavity. Intervals where the function is concave up. What tells you about concavity? The second derivative. I'm going to be concave up when my second derivative is what? A positive number. So I have to look here on my second derivative row for all the places where the second derivative is a positive number. So here and here, right? So second derivative, positive. So from 1 to 2 and from 4 to forever? Yeah. From 4 to forever? Concave up. Okay, so let me fill that in here. Concave up, concave up. This was decrease, 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 increase. Okay, concave down. Concave down when what happens? Second derivative is negative. Okay, so I've got one here, 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 and here. So we're going to say concave down from negative infinity until 1. That's that first interval. And from 2 to 4. What is an inflection point? Remember from Monday what an inflection point is? What is an inflection point? An inflection point is in a place where the concavity changes. So it's a place where concavity changes. So the concavity changes direction here when it goes from concave down to concave up. And then again here, where it goes from concave up to concave down. And then again there, where it goes from concave down to concave up. So I have 3 inflection points, x equals 1, x equals 2, and x equals 4.
That's where the second derivative equals 0.
It's where the second derivative equals 0, but remember over here, when we did the extrema, it wasn't enough for the second derivative, for the derivative to just be 0. It had to actually change increasing or decreasing, right? So inflection points occur at critical points of the second derivative, but it has to change concavity there. In this example, it changed at every 0, but that might not always be the case. Okay, I want to continue these little shape things underneath here because I want to draw the graph of a function that has these properties, okay? So I think the easiest way to do that is to make these shapes and then squish them together into one picture. So on this interval from 1 to 2, what shape am I making? Decreasing, concave up, looks like like this, right? Yeah, like that, like this. Maybe this is the funnest part about the roller coaster. I don't know, which is the more fun of the roller coaster. This one where you're falling straight down or where you're like rounding up at the bottom. Yeah, you like the loops. I don't like the loops because I think I'm too short. My ears bang the sides. Okay. Here I am from 2 to 4. What's happening from 2 to 4?
Okay, now.
Concave down and decreasing. What do I look like if I'm concave down and decreasing? You're going to go home and do your homework. Your parents are going to be like, what are you doing? Why are you making those shapes? Okay, here I am from 4 to 5. Decreasing and concave up. That's the one we just did, right? The roller coaster one. Okay, last one after 5. Increasing. That's nice, finally. Increasing and concave up. What do you look like if you're increasing and concave up? Yep, I like that one, like that. Okay, so I'm going to try to put all of these pieces together and draw a graph. I'm going to do it on the board first so that I can see the pieces, and then I'll put it in the notes. Okay, what numbers do you think I should put on this number line? The places where things were changing, right? -1, 1, 2, 4, 5, right? All those places where something happened. -1, 1, 2, 4, and 5. That seems a little bit far away. Let me squish that a little bit together. So. Okay, remember, I know nothing about like how high or low this graph goes, right? I just know like its basic shape. Okay, before -1, I have this increasing concave down shape, kind of like that. Between -1 and 1, I have to put this guy on there. So I'm going to put him in there like that. Yeah. From 1 to 2, I need to keep going, but change concavity like that. At 2, what happens? Keep going down still, right? Do you see this? I'm here at this one at 2, still down more. Change concavity again. Here I am here from 4 to 5. What happens? Down more. Finally, when I get to 5, I go up. Forever. That's a pretty fun roller coaster ride, I think. Right? Probably the Great American Screen Machine does that.
Which one's that?
Yeah, you're gonna go up forever and you have to land on the moon.
Is that the wood one?
The wood one? Yeah, like in the
The one
front.
really bad.
The wood one in the back is the worst one, but the one in the front is not too
Oh,
bad,
that's
right?
good.
Isn't that the Great American Screen Machine, the one in the front?
They changed it.
Did they? Haven't been there in a while. COVID. Okay, let me try to draw this picture on my note sheet for the viewers at home. I should have started up higher. -1, 1, 2, 4, 5. Hope I have enough space below here. I do. Okay. I need this.
Yeah, it's top.
and then this, and then this, and then this, and then this, and then this. Okay, I have a maximum there. I have the minimum there. This one guy was an inflection point. This guy's a horizontal tangent line. That guy's an inflection point. So inflection, inflection, min, max, nothing. I guess this guy's an inflection, don't you think? Concave up, concave down. Yeah.
This is the graph of f(x), right?
This is the graph of f of x. Yeah. Graph of f of x. That would have been really hard if I hadn't had that sign chart and drew those little pieces so I could just squish them together, right? All right, let's try again. You got to do a lot of thinking this week. You can do it though. I have faith in you. Right? That's what happens. The following figure gives the graph of the derivative. Do you see it bolded? It's bolded there. That means important information. The following figure gives the graph of the derivative. This is not the graph of the function. This is the graph of the derivative. Okay, so which column are you using on our chart from the first page? The second one, the one in the middle that tells us all the things about the derivative, right? So this is the graph of the derivative. You're using all the information from the middle column. Okay, I'm going to scroll back up to the middle column for a second in case people didn't get to write that down. I am using all the information about the middle column. Really, when I have graphs, I'm using this stuff at the bottom, okay? So it says, when my first derivative is above the x-axis, my function is going to be going up. When my first derivative is below the x-axis, my function is going to be going down. When my first derivative is going up, my function is going to be concave up. When my first derivative is going down, my function is going to be concave down. Okay, we got that? That's the important information of today. This chart is super important. If you print nothing, print that. Okay, here is the derivative. I'm going to make a sign chart just like I did before, okay? So I'm going to make a column for f prime, a row, excuse me, and a row for f double prime. What numbers do you think I should put on here? -1, 1, and 3. Yeah, that's what you meant. X equals -1. X equals 1. X equals 3. I didn't have enough room. I did a bad job. Do a better job than I did. I don't have enough space. I have to squeeze it in right there. It's fine. I can do it. Okay, so before -1, like this, between -1 and 1, and between 1 and 3, and after 3. Okay, at -1, the first derivative was 0. You see that right here? At -1, this graph, the first derivative is 0. At 3, right here, the first derivative is 0. Because remember, this picture that we're looking at is the first derivative. This picture is not the function. This picture is the first derivative. So it crosses the x-axis at 2 places, and it's 0 at those 2 places. Okay, before -1, is the first derivative a positive number or a negative number? Negative, because it's below the x-axis. Negative. Okay. Between -1 and 1 here, is the first derivative a positive number or a negative number? Positive, because it's above the x-axis. At 1, is the first derivative a positive number or a negative number? Positive, because it's above the x-axis. Yes, exactly. I know. Between 1 and 3, it's still above the x-axis, still positive. Okay, after 3, below the x-axis, negative. Okay, let's do the second derivative. Yeah, I'm gonna scroll back up to that chart for a minute. You guys were looking anxiously, but I was like, are you still writing or are you just watching me? Okay, here I am right here, right? When the first derivative is going up, the second derivative is positive, the function is concave up. When the first derivative is going down, the second derivative is negative, the function is concave down. When the first derivative is going up, here, the second derivative is positive, the function is concave down. So positive, positive, positive. At 1, the second derivative is going to be 0 because that's a critical point of the first derivative. After 1, the first derivative is going down. So the second derivative is going to be what kind of number? Negative, negative, negative. Okay, I made my sign chart. Below here, I'm going to put those little shapes. Okay, what I'm going to do now is completely ignore this picture. I am ignoring this picture because I gained all the information I needed from it and put it in my sign chart. And it's much easier for me to read my sign chart than it is to try to interpret this picture. So I took the picture, I interpreted it and made a sign chart. Ignore the picture now. Here I am in this first interval. My first derivative is negative. My second derivative is positive. The shape I have is?
No.
My first derivative is negative. So I'm doing what? Decreasing. My second derivative is positive. So I'm concave up. So decreasing, concave up, like this. Decreasing, concave up. You could write that down here if you wanted to. Decreasing, concave up. Okay. Between -1 and 1, I got 2 positives. 2 positives. So I am increasing, concave up. Yep, that one. Increasing, concave up. This guy. Okay. Between 1 and 3, I have a positive and a negative. So I am increasing, concave down. Like that one. Yep, you got it. Increasing, concave down, that guy. Okay, the last one here is negative, negative. Decreasing, concave down. Good. Decreasing, concave down. Okay, down here, I'm going to draw the picture of my function. Function. F of x. Okay, I'm going to put -1. I'm going to put 1, and I'm going to put 3. Okay, I need to be like this, and then like this, and then like this, like crisscrossed, and then like that. Okay, so I have a minimum here at -1. I have a minimum because I am decreasing and then increasing. I have a maximum here at 3. Let me move this guy up a little bit so he doesn't get in the way. There. Do I have any inflection points? At x equals 1, I have an inflection point at x equals 1. I was concave up before x equals 1. I'm concave down after x equals 1. So I have an inflection point there at x equals 1.
You said it's a little inflection.
Yep, I just wrote inf. Inf. Put there too. Input. Okay, I got one more, I think. Yep. I got one more. Sketch the graph of a function that is continuous. What does it mean for the graph to be continuous? No breaks. Doesn't have to be differentiable. Could have some cusp, right? But no breaks. So there can't be any asymptotes, right? There can't be any holes. Okay. It has the following properties. Okay, it tells me that a lot of things are zero. You see that? F of -6 is 0, f of 2 is 0, f prime of -6 is 0, f prime of -2 is 0, f prime of 2 is 0, and f of x is greater than or equal to 0 on the whole interval. What does that mean?
It never crosses.
It never crosses the x-axis. It stays above the x-axis the whole time. This guy at the end here tells me it's above the x-axis the whole time. Okay, so I'm going to draw my x-axis way down here. I'm going to draw my y-axis here. X, Y. What points should I put on this graph? -6, I like that one, yeah. What else? -2, yeah, I like -2. What else? 2, did I hear someone say 2? 2, yeah, I like that. Okay. What do you know happens at -6? What? It equals 2. No, it equals f of 2. Look here. It equals 0, right? It's on the x-axis here. Is the graph on the x-axis anywhere else? At 2 here. Because of these two guys right there. F of -6 and f of 2 equals 0. So the y value at -6 and the y value at 2 is 0. What do these next three things say? F prime of -6, F prime of -2, and F prime of 2.
The slope is 0. So it's
The slope is 0. So those are critical points, right? They might be maximums, they might be minimums, or they might be flat points. So these three guys here are going to be critical points. Maybe maximums, maybe minimums, maybe flat points. Critical points. Okay, so at -2, I need like a flat point. Maybe a maximum. Maybe I'll put a maximum there. Okay, but I'm going to put it here. I am definitely going to put a maximum there. How do you know that -2 is going to be a maximum? I got to get back down here, right? So I got to get down here. And I got to get up to the yellow point at -2. I don't know where the yellow point is, but it's somewhere, right? I got to get back down to 2. And then I'm going to go back up. How do I know I'm going up on both ends? Because it's always above the x-axis. Yeah. Okay, here we go. Good luck. I'm going to do this. That was bad. I'm going to go like this. I told you I needed luck. I'm going to go like that. And I'm going to go like that. This one's bad. Pretend that one's nicer than this. There. I made him nicer. I didn't, but I made him nicer. It looks kind of like the upside down version of the graph we did earlier. Right? This one didn't give me very much information, right? It didn't tell me the concavity anywhere. It didn't tell me where it was increasing or decreasing. It told me some information about the y values, which I hadn't seen before. But, you know, I had to interpolate a lot of information there. Okay, I am in the AEC until 3 o'clock today. You're welcome to come down and finish up your homework. Friday is a homework question answering day. And then remember, Monday is a recording day. So it's actually already ready, but the recording will be up for Monday with the filled in notes. So you can watch the recording and fill in the notes as you go along. All right. See you soon.